the like optoelectronics. I'm going to describe more like what we work on. I did my bachelor's from IIT Kharagpur, did my PhD from Stanford, and then I worked in UC Berkeley for 1 year as a postdoc, and then Intel for 1 year, and for last 7 years I'm at University of Washington. And we have several different research directions. When I give the talk, I'll kind of tell you about all of them, including some on the quantum optoelectronics. Okay.
Thank you so much, sir, for giving your valuable time for our participants, and hope the participants will be benefited from your session. So we are eagerly waiting for your talk. So please proceed, sir.
Okay, good. So can you guys see my screen?
Yes, sir.
Yeah, yeah. It's
Screen is
wonderful.
Oh,
visible.
Okay.
okay, great, great. Okay, thank you, and thank you for the invite. So I'm going to talk about some of the work that we are doing on the field of quantum optoelectronics, including something on the photonic quantum simulation. And it's I know like this is more on the hardware side and a little bit more physics oriented talk. Some of like what I'm going to tell you, like what kind of photonic engineering is possible, what what is the kind of big challenges in the field, and then I'll show you like how actually that might help with some of the quantum simulation problem. Okay. My name is ArkaMazumdar, as I mentioned. I am jointly affiliated with Electrical and Computer Engineering and Physics Department here at University of Washington, Seattle. You can know more about my lab, my research, all the papers that are published. Everything is in my group website. And if you have any question about my talk or in general about my group, you can email me at this email ID. Okay. So first, let me just kind of maybe acknowledge my team. This is a Zoom picture for my whole group and alumni during the Christmas break, and the different funding agencies, including federal funding as well as a lot of funding from the companies that supported all my research in general. And yeah, feel free to stop me if you have any question, and I'll probably stop in between just to kind of see if you have any questions about the talk. It's better to kind of clarify while we are going rather than keeping all the questions for the end. Okay. Okay. So in University of Washington, my lab is called Nano Optoelectronic Integrated System Engineering, and what we are really kind of understanding the physics of interaction between light, or if you think about the quantum particle of light photon, and matter, which are made of electrons. And to do that, we design and fabricate various nanophotonic structures. So these structures have very, very small length scale patterning. These things are patterned using electron beam lithography machine. And we make something that's known as photonic crystal cavity, ring resonator. We work with meta optics. And on those photonic structures, we integrate new material. Okay. For example, one of the big direction in my group is working with atomically thin material like graphene, but this material actually hosts something called excitons, which is like an artificial atom, which I'm going to discuss what those are. We also work with phase change material, some organic material, quantum dot, different kind of complex oxides. So my group studies various different materials. These materials comes from many of my collaborators. We design and fabricate these photonic structures, and this hybrid system that we develop using light and matter. In my group, we are pursuing 4 different research directions. So one of the research direction is hybrid integrated photonics. So this one has some connection with quantum, but I'm not really going to focus on the quantum aspect. For quantum aspect, I'm primarily going to talk about this quantum many-body simulation. But hybrid integrated photonics, the idea is like integrated circuits. By using integrated photonics, we can make very, very small chip scale optical systems. And this work we are currently doing in collaboration with Intel and several other companies. And the idea is that can we actually use new materials like phase change material integrated with the silicon photonic structure, this integrated photonic structure, for very high speed data communication. And it turns out that many of these platform that we are developing can also be useful for quantum. So you probably heard about some of the work from Xanadu. There's a startup in Canada also Psi Quantum. That's a startup in Palo Alto, which is next door to Stanford, and they are developing this quantum computer using integrated photonics, and some of the technology that we are developing can also be used for this kind of quantum computing structure. Another direction that we are doing is nanophotonic computational image sensor, and the idea is using nanophotonic structures, this new kind of optical structures, and computational backend. That computational backend involves some kind of deep neural network. It can be some other kind of artificial intelligence. Together, can we actually create very, very small sensors? And some of this work that we are doing, one of the key result that we recently have is we can break the bandwidth limitations that sometimes you have in the diffractive optics. The diffractive optics has a color problem because these are wavelength scale structures, so it's a it has very strong chromatic aberration. We can solve that using meta optics or meta surface plus computational backend. Now, connected to this, we are also looking into can we create an optical neural network, a neuromorphic network using light. So we all know about deep neural network, and deep neural network are essentially based on like these are all implemented in the software. But if we can implement this using hardware like optical system, can we actually use that for making very, very fast AI and machine learning platform? One of the direction that we are also looking into, that can we bring the nonlinear interactions? We all know that in the deep neural network you need some kind of nonlinearity like softmax or ReLU like nonlinearity. We can bring this nonlinearity to optical domain, then you can really have several orders of magnitude faster neural network or energy efficient neural network. Now, if you take this nonlinearity that we are trying to bring in optical neuromorphic computing, if you can make it to very, very strong and go to a single photon level nonlinearity, you can start seeing signature of quantum mechanics. And this kind of what I'm going to primarily talk about today, that can we do quantum many-body simulation with photons? Okay, so using photon as a qubit, can we do quantum many-body simulation? And as you saw in my title, we talked about two words, quantum simulations. We are still developing technologies, but I'm going to tell you what are the challenges and how we solve some of the challenges, what are the challenges remain. So that will be primarily focus on today's talk. Now, this I'm not really going to talk about this other three research because they don't really connect to the quantum aspect or quantum computing. But if you are interested, I'll be happy to talk maybe after this seminar, or you can send me an email. But again, all the papers on this is out there. I also have given various talk on this topics. Those the videos of the talks are in my website, so you should be able to see it if you are interested in this other aspect of my research. Okay, so let's start with the quantum computing, right? So we know, and this is a figure from another paper where that we have now full stack of quantum computing, right? That there is not just the hardware. There are many layers of this quantum computing. My research really falls into like in the really bottom layers, the physical systems. That's what we are working on. And as I just mentioned, the Xanadu, also some work from China. That from Professor DP Professor not DP yeah, the DP group. They have some work on really boson sampling system. There you are using optics as a qubit. So optics can definitely provide qubit, but optics can also provide the infrastructure for scaling. So if you look into currently, by the way, it's Jianwei Pan, I forgot with DP the Jianwei Pan's group for this boson sampling work, that they're using optics, optical qubit. But as I mentioned, that optics can also provide the infrastructure for scaling. If you think about current laptop, like you have, of course, microprocessor, but there are many different things that you need to actually create a computer. And it is pretty clear that optics will play a very major role in some way, either connecting different quantum computer. Maybe this quantum computer will be built with ion trap or superconducting system. To connect them, we need optics. But even in between, connecting like different bits, you might need optics, right? Changing this ion trap, if you know about the ion trap quantum computer, you need multiple beams that comes in, and these multiple beams has to change these different ions. So there is a huge amount of laser and resource for optics are needed. And I think it can be very easily said that the role that silicon played for classical computing, integrated photonics are going to play for quantum computing. So really this miniaturization, making it scalable, optics is going to play a very, very important role. We have one project, and again, this is it won't be my main focus of today's talk. Today's talk will primarily focus on light as a qubit, and if we can engineer nonlinear interaction, what we can do. But as I meant, like as optics as a resource for quantum computing, we know that this ENIAC 1943, this was the big room full of vacuum tubes, and we have this personal computing today. And in between, of course, there were like this time when people started realizing that we can start making some of these transistors on chip, right? And if you look at today's system, like this is kind of what quantum computing looks like today. It's a really big optics full of optics table full of optics. It's pretty large, but we want to go here, right? I mean, that's kind of the vision, that we will have this kind of rack mounted the noisy intermediate state quantum computing. Maybe we have many of them, and one of the missing piece for this problem is, as I mentioned, that how do you actually control that many optical beams? You need like thousands of a million optical beams to be controlled, to control many atomic qubit or ion trap based qubit. And integrated photonics really provides a solution, and we are actually working on a very big multidisciplinary project with Berkeley, Sandia Lab, and some other startup in quantum computing to develop a technology on integrated photonic based platform, so that we can bring this whole optics that made of optical table full of optics to on chip. Okay, but as I mentioned, that these are, again, it's a peripheral where optics is really being used as a resource to scale up quantum computing. We are going to talk today is how can we use optics as a qubit, and kind of the application that we are primarily interested in is quantum many-body simulation. And the question that we ask, okay, can we do quantum many-body simulation with interaction between light? Okay? So we all know that there are many different kind of strongly correlated materials. So strongly correlated materials essentially means that this system, the materials are made of electrons, but these electrons are of course interacting by Coulomb force. And this interaction, the signature of interaction, shows up in some mesoscopic properties of the material system. One of the hallmark signature is, of course, fractional quantum Hall effect. So this fractional fraction that happens in this quantum Hall effect comes from the strong correlation between the electrons. You can all think about high TC superconductivity. That's like one of the probably really not well understood problem in condensed matter. So strongly correlated materials are very important for several different condensed matter systems. And it's very difficult to really understand that how these materials work, because quantum mechanically, if you start simulating every electron, the system just becomes huge, right? And that's where quantum computing or a quantum simulator can play a very important role. And this is kind of really the idea that Feynman proposed, that can we simulate a very complicated quantum system with a simple quantum system. And the simple quantum system, the main thing is we can control this simple quantum system. We really know that what is going on with each like we can control different part of the Hamiltonian, different coupling strength, and then we can simulate that how this strongly correlated system is going to behave. And to that end, this kind of quantum simulation is being pursued by various different quantum objects. Right? There is work in neutral atom in optical lattices, arguably one of the most well developed platform where quantum simulation is happening. People are also looking into superconducting circuits, but there's also arrays of quantum dots, polar molecules, arrays of cavities, and arrays of trapped ions. And in most of this system, what you really need to identify is what is that particle that's mimicking the behavior of electrons. So electron, as we know, is a quantum particle. They behave like a wave quantum mechanically. They also have interaction. So to mimic this behavior of electrons, we need to have another quantum object, and for the neutral atom is the atoms of the object. For trapped atoms, ion is the object. Superconducting circuit, it's the trans-1 qubit is the object, right? Now we want to understand that is it possible to use light to do the quantum simulation? So light as a qubit, okay? So why light? I'm going to explain in a bit, but the problem that we are asking ourselves that is it possible to do non-equilibrium quantum simulation? So it's not just quantum system, it's a quantum system that's not in the equilibrium. So it's a driven dissipative system. What it means that, like, just think about like your circuit, right? An RC circuit. That's a driven dissipative system because you have to apply a battery. That battery is essentially putting charge in, and the charge is going to get dissipated in the resistance. So similarly, in quantum world, right, we can also have systems which are which are in non-equilibrium, which are not in equilibrium. So can we actually start simulating those using correlated light? And there are a lot of theoretical work on that. You can see these references here, and this theoretical work, people actually have looked into this, that we can actually do quantum simulation with correlated light. And in all this theory work, and there's a very little work in experiment, and I'm going to explain that what are the challenges and how can we solve it. So if you look into that, what is the system that we need to really engineer? It looks like an array of coupled cavities. Okay, so array of coupled nodes. In each node we have light. Light can go from one node to another node just by, because it's electromagnetic wave. It can go from one place to another place. It just can travel. But at each node, we need a very, very strong nonlinearity so that photons start interacting with each other. Okay, so you probably already know this, but photons do not interact with each other. And if you ask yourself, okay, how do you know that photons do not interact with each other? Just think about like anything that you are watching or seeing. If you draw rays from that particular object to both of your eyes, you will see these rays are going to cross at some point of time. So two light rays cross and come to your eyes, but this crossing doesn't really change anything on the light. So if you think about it, you just put like electrical wire from some point to your both of your eyes. The moment two electrical wire connect each other, electron can go from one wire to another wire, right? So the electrons are very easy to kind of interact with each other. They can affect each other much more, whereas light, they do not affect each other. But we really need to engineer some things, and that I'm going to mention how can we engineer that so that there is a very, very strong repulsive interaction between electrons. And what it means that if you have one photon, let's say in a node, if you want to put a second photon, you have to pay some energy cost. Okay, so the energy cost is kind of some more technical term from the physics side, but it essentially means that a same frequency of photon cannot really stay there. So that's how you have a repulsive interaction. And think about electrons, that we know that from Pauli's exclusion principle, if you have one electron, the second electron when it comes here, that they cannot occupy the same state. We have to have the same kind of properties for light. So that is the one thing that we have to engineer. And light goes from one node to another node pretty easily, so that we kind of go get it for free. So then the question that we should ask ourselves, that why light, right? That why not, like, what is so unique about light? And there are like essentially two reasons in my opinion. One is the optical systems are inherently a driven dissipative nature. Just provide a platform to study non-equilibrium physics, which we cannot really do easily with other platforms. I'll mention though the superconducting system, most of the work that's going on in the superconducting system platform for quantum simulation, and it's good to know that superconducting system has a lot of work going on in the quantum computing as well. And quantum computing definitely has some similarity with quantum simulation, but there are some work that's specific to quantum simulation, quantum many-body simulation using superconducting qubit. And the superconducting qubit system, this quantum simulation, also are essentially driven dissipative nature. And in some way there is fundamentally not much difference, because it's both are photon, both are electromagnetic wave. One, the optical photon is just at extremely high energy, like 10 to the power 5 times more energy than a superconducting photon, but they are still photons. But this high energy essentially comes to the second point, that we can really detect single photons. We have equipment. We have some equipment in our lab, and it's pretty easy to get in nowadays. We can measure multi-photon correlation. So not just one photon, we can measure many photon correlation, and that photon correlation gives us a way to understand that what quantum system we actually have. Okay, so almost no one has measured multi-particle correlation. Okay, with any other system, and light you can measure multi-photon correlations. We in some of the work that I did several years back, we measure up to 3 photon correlation. In this work that in this the boson sampling work, you are actually measuring extremely high number of photon correlation, and that is actually possible. But if you think about superconducting system, measuring this kind of high number of photon correlation is not straightforward. So these are the two reasons why we believe that light actually can be pretty interesting for doing quantum many-body simulation, this non-equilibrium quantum simulation. Okay, so what is the kind of the Hamiltonian that we are talking about here? So we have a couple cavities, right, a couple node. Okay, so our Hamiltonian, we are going to assume nearest neighbor coupling for something. We can also engineer not necessarily nearest neighbor coupling. So your first term is going to look something like this. So probably you already have some exposure to quantum mechanics, and I know that you are in this workshop for whole week. The first term essentially tells you this the creation times annihilation operator. So it's the number operator for photons, and the delta I is the energy. In this case, that what is the cavity energy or the node energy. So every node can hold a single mode. Okay, what is that mode frequency? And then we get a number like this. Okay. Then we have a coupling between this, and photon just coupled to each other. It's the nearest neighbor. Just by photon leaks from one point to the another point, it's a wave, it can travel, and that's how you can have a coupling. So you can have an Hamiltonian that looks like this term. So your T sub I is the tunneling rate, and that's AI dagger. AI dagger is you are essentially creating, let's say this is my I and this is I plus 1. If your photon goes from I plus 1 cavity to ith cavity, you get this term, but it's reversible, it's a coherent dynamics. So you can also get photon from here to here, that will be the second term. Okay, and finally I have a nonlinear term, and this is the nonlinear term that I was saying is what it gives you is the effective interaction between photon and photon. And you can show here, like this term, if you rearrange by using the well-known commutation relationship that AI dagger minus AI dagger AI is equal to 1, you can see that this term is given by the number n times n minus 1. So when n equal to 1, so if you have a photon number of 1, that this term vanishes. But if you have n equal to 2, you have a significant amount of term that you are adding, and that is the energy cost you are paying. As I mentioned, that Hamiltonian essentially tells you the energy of the system. So if you just think about, like, you have 1 photon, your energy is omega, 2 photon energy is 2 omega, and that's what you'll get from this term, right, the first term. But this term tells you that just because you have 2 photon, it's not just 2 omega, it's a 2 omega plus some other term. So there's the energy cost you need to pay. Is kind of more physics way to think about it, but in another way to think about it is like if you put 1 photon, a same energy photon cannot really couple there is a strong interaction. Okay, and with integrated photonics, I'm going to show you some structures. We can actually do arbitrary coupling, so it's not just nearest neighbor. We can couple multiple different cavities. They are far off. We can put optical waveguide, and using waveguide we can couple them. So this is kind of the Hamiltonian we can implement. Okay, so I already kind of mentioned cavity, but let's think about this as a node. By node, what it means that you actually have a specific mode. That mode has a well-defined frequency, well-defined mode profile, well-defined spatial distribution, and that we can abstract it out as an annihilation and creation operator for that particular mode. Now, in reality, these modes can be implemented using a cavity. Okay, and this essentially brings us to this idea of cavity QED, which I'm going to spend some time on. Okay, so think about each of this node is actually an optical resonator, and that resonator has some kind of atomic system, and this atomic system in solid state platform will be some sort of maybe NV center or quantum dot, And what we are working with is a solution process material and 2D material. So these are a little bit different kind of material. These are broad emitter, but these are highly scalable. You can put this material in every cavity, and that's kind of one of the reason we are focusing on this kind of new material system compared to like the defect centers that many other people work on. Okay, so this cavity QD, essentially we have an atomic system inside a cavity, and this system has three important rate parameters. One is the G, that is the coherent light matter interaction strength, and then we have a loss from the cavity which is given by kappa, and we have a dipole decay rate that's given by gamma. Okay, so in this kind of cavity QD system we have one interaction strength and we have two loss term, right? It turns out that interaction strength, I'm not going to derive it, is proportional to the dipole moment of this atom, sometimes also called an oscillator strength, and inversely proportional to the mode volume, square root of the mode volume. Okay, many of you probably have know this experiment that if you take a piece of paper and you take a magnifying glass in the sunlight and you focus your light on the paper, you are going to burn the paper, right? What cavity does is something very similar. So if you are think about this, that if you just put the paper and the magnifying glass is not focused, you are not going to burn it. So you have to focus it, and focusing essentially means that you are taking this energy, all the photon that's incident on your magnifying glass, you're putting it on a very small focal spot. So that's what we call spatial confinements. We are spatially storing light in a small spot, and then you need to hold it for some time. It doesn't really happen that you focus it and you start burning immediately. So that means you also have to hold the light at that point for some amount of time. So you need both spatial confinement and temporal confinement. So confinement both in the space, that means like what is the volume over which the light is confined, and the time, that how much time, how long you are holding the photo. So this how long is given by this term kappa, which is inversely proportional to the Q, is called the quality factor, as the cavity decay rate, and gamma is the exciton decay rate. And this system, it can be really you can think about two oscillators. So just two LC oscillator or two mass spring model that we learned in like our basic high school physics, right? If you have a one mass spring system, another mass spring system, both have some omega frequency, let's say. If you put another spring in between these two mass, then you couple them, and then your frequency actually becomes like it's no longer omega. You get two frequency, right? One of the frequency where this two mass goes like this way, that's the common mode, and the other case it goes like into two different ways, right? So you get two different modes, and this is the same physics here, like in a level, like these are two oscillators that are coupled to each other. The only difference here is that this one of the oscillator, the material oscillator, is actually a material system. It has an electronic system, so it actually has this interaction like between electrons. So we are still going to use photons and as our qubit, but we are going to use a material system to mediate some interaction between two photons. So photons don't really interact with each other, but to mediate this interaction, we are going to create a light matter interaction. So interaction between photon and electron of the material, and another photon and electron from the same material. And by engineering this to light matter interaction, we are going to effectively create a photon-photon interaction. Okay. So this interaction strength G, when it's greater than the system losses, kappa and gamma, we reach a regime that known as strong coupling. Okay. And what's happening in this strong coupling regime is this exciton, or sorry, this atomic system. I'm going to bring what is exciton in a bit, but this atomic system is a two-level system, or think about an electronic system, mixes with photons and creates a new particle called polariton. So this polariton is half particle or half material and half light. Okay, it preserves the goodness of light because it can travel from one point to another point, but it also has the interaction coming from the electronic counterpart of this material. So you can actually have very strong polariton interaction, which is much stronger than just photon-photon interaction. So that's what happened in the strong coupling. And if the other case, you reach in the weak coupling regime, so if G is less than kappa gamma. So this weak coupling regime is actually used for creating single photon source. So many of the quantum algorithm that you need in physically, if you run in optics, you need single photons to start with. If you remember this work by, again, for the Gianwepan's boson sampling, you have to generate single photons, and he generated a single photon in his recent paper using spontaneous parametric down conversion, the nonlinear optical effect. But you can also do it with the two-level system, kind of a quantum dot. And using cavity, you can enhance that rate at which you are generating the photons. Okay, so there are two kind of coupling regime, and in cavity QED we have two different regime. That is like according to cavity QED language. One is the bad cavity regime. Bad cavity regime is defined when the emitter is very narrow. So the gamma, the loss rate of the exciton, is much larger, smaller than the cavity decay rate. Okay, so if you think about in the time domain, that your gamma is actually decaying slower than the cavity. That means when you go to your Fourier domain, your cavity has a broader spectrum than emitter. Okay, so cavity is actually going to decay much faster. So when you take a Fourier transform, right, it's going to be broad. Atoms, semiconductor quantum dots, different kind of defect centers like NV centers, silicon vacancy centers work in this bad cavity regime. Okay, and in this kind of case, we actually really need to tune each emitter. So for quantum simulation, as I mentioned, that we need all those nodes, but all these nodes has to be identical. Okay, so that means every node has to have same frequency, and this nonlinearity that we have in each node, they also have to occur in the same frequency of the same strength, which essentially means each emitter has to have the same resonance frequency, which boils down to that we need to tune each emitter for quantum simulation. Okay, which turns out to be actually a very difficult task to do, because these emitters are very difficult to tune. You need very sophisticated electronics. When you put electronics that close to optical system, the metal actually kills the quality factors. There are a lot of challenges that people are trying to solve in this problem. The other regime, which in my opinion is relatively unexplored in the quantum optics community, is called the good cavity regime, where the emitters are actually broad. So the emitter decays much faster than the cavity decay. So gamma, the exciton decay rate, is larger than the kappa. That again, from Fourier transform, essentially it means the emitter is broader than the cavity. An example of some of these things are quantum well, solution process material, which is also known as colloidal material, and the 2D material. 2D material is the atomically thin material. So these materials actually, and the exciton, I mentioned this term here. Excitons are is an electron hole bound pair, and for all practical purposes, let's think about exciton is just an atomic system. It's an artificial atom. Okay, I'm not going to go into more details of what exciton is, what is the physical significance, but for this work, we are going to assume, and every exciton has a ground state when the exciton electron hole pair are not formed, and when you form this electron hole pair, that's my excited state. So it's a two-level system. It behaves like an atom. Okay, but in this case, as the emitters are broad, you actually have a really overlapping of the emitters. So just by changing the cavity resonance to have same frequency, you should be able to get the same similar atomic light matter interaction in each cavity. So that's kind of the key insight which we are going after, that if we actually have a broad emitter, then we can just change the cavity resonances. And there are multiple different ways to change the cavity resonances, which I'm going to discuss, which might be more easier to do than changing the atomic resonances. So if you do that, then we can probably we can get into a regime of quantum simulation where we have many cavities, all the cavities are at the same resonance frequency, and then we have the nonlinearity. Okay, so I mentioned that most of the work in this kind of optical quantum simulation has been on the theoretical side. Very little, if not none, experimental signature that has been demonstrated. And why is that? Okay, so there are, in my opinion, there are three challenges for any kind of photonic quantum simulation. And I will argue that these challenges are actually same for any kind of quantum system. But I'm going to focus primarily on the quantum from the optical systems. So first is scalability. So you probably heard many times that one of the big problem right now in quantum computer is how do you make a large quantum computer? You can make a quantum computer with 50 qubit. We know that Google made one. Of course, there is some, like, it's very limited in terms of functionality, but at least there is a 50 qubit quantum computer. Scaling it to our 50 physical qubit quantum computer, not 50 logical qubit. So if you want to scale it to like a million physical qubit, it's just there is no way you can do it. Similarly here, what it boils down to, if you really want to have that many quantum system, you need the large number of optical cavities. Now optical cavities are essentially two mirrors. You put two mirrors, and that those two mirrors create your optical cavity. You learned it probably in some kind of basic electromagnetics that we calculate the eigenstate of this system. We have two mirrors, we solve the Maxwell's equation, and then we say like field has to go down to 0 here, field has to go down to 0 here, and we calculate, okay, what is the mode profile for this cavities. Okay, so those are big. So how do you solve it? You put it in a solid state system, right? Put it in an integrated photonic system, and we can make many cavities. So this is an example of 16 cavities optical resonator that's fabricated by my group. Actually, it's fabricated by me when I was in Stanford. You can see the size. These are very, very small. Just to give you an idea, this is the length scale. It's 1 micron, and your hair thickness is around 100 micron. So this structure, so within 100 micron, we can fit like many, many cavities. So the solid state does provide a good solution in terms of scalability. But all the resonators should have same resonance frequency and high quality factor. So this essentially means to have the same resonance frequency, you have to have some tuning mechanism for each cavity. Because even if we fabricate this structure with the world's best fabrication process, we still have some limitations in terms of like at least 5-6 nanometer line width. That is, like all the resonance will not be in the same way because we have fabrication imperfection. Tunability. And this basically boils down to the previous problem that we really need to tune each resonance, but we also have to figure out, okay, how to tune the coupling strength, right? I mean, because as I mentioned to begin with, that this goal for quantum simulation, that we are going to use a simple quantum system, but we have to have control over each term in that Hamiltonian. That means resonance frequency, coupling strength. How do you do that? That turns out to be very difficult. But I think the elephant in the room is how do you get this interaction? So I told you already that the photons do not interact with each other. We need this photon to interact, and not just interact. You have to interact in the single photon level. That's an extremely difficult problem to solve. Okay, that we really need to make sure that two photons talk to like interact with each other, and it turns out that it's very difficult to do. Okay. So I'm going to spend a lot of time explaining what the single photon nonlinearity is, because the single photon nonlinearity will be useful for the quantum simulation, and it will be good to kind of understand that what I mean by the single photon nonlinearity. Okay. So let's start with a simple harmonic oscillator. Okay. A simple harmonic oscillator that we all know, a linear cavity behave like a simple harmonic oscillator. Okay. All our energy states are equispaced. So we have a ground state, then the first state is at omega, second state is 2 omega, 3 omega, 4 omega, right? That's what we learned in very simple quantum mechanics when you do the simple harmonic oscillator model. Now what happens when you introduce a material system, and let's say you introduce a, like, can be a two-level system, can be any other excitonic system, you shift each layer, each energy level. So omega naught is, let's say, omega naught. But 2 omega naught, as I mentioned, this U term gives rise to some extra energy. 3 omega will give rise to another energy. Okay. Now, these lines that I'm drawing, right, it's not like really a single line. In physical system, there is a broadening because everything has a loss, and loss is exponential decay. You take a Fourier transform, you get like a Lorentzian line shape. So every line that I'm drawing as a delta function is actually not delta function. It has some specific broadening. So when you have this broadening, then if your change in the energy, the delta E1 or delta E2 is larger than the broadening, then if you couple one photon, let's say here, the second photon will go to the somewhere in delta E1, like 2 delta E1, but that is not going to couple to this level. So that's what I mean by the anharmonicity or nonlinearity, that we are going to shift this energy level for each layer by a certain amount, and that change is larger than the system losses. Okay, how do we measure it? So the way we measure it is known by something that known as Hanbury-Brown twist setup. We measured the second order correlation of the photons. So the experiment that we do, that we have a cavity with an emitter, we shine light and we collect the light on the other end. We take that light, we send it to a beam splitter. So in optics, beam splitter essentially means it's a 50% reflective mirror. Half of the light goes in this direction, half of the light goes in this direction, and then we put two detector. The detector actually gets the detection, like count the photon, and we measured the coincidence between these two detectors. Now think about if you have a single photon coming, the single photon can either go here or here, because a single photon is not divisible. It cannot be half photon, half photon. I mean, that's what it means to have single photon system. So you will never get a coincidence, and this whole correlation that we are measuring is given by this autocorrelation function. This is the expected value of this term, and you can calculate when tau equal to 0, the G20 becomes 0 for a hardcore boson system. The hardcore boson means that this third energy is so high that you can just assume that this is a two-level system. Okay, and that's what we need for many of the quantum simulation. Ultimately, it's two-level system, because that's when you have two-level system, you can start thinking about modeling a spin physics using this two-level system. If you G20 equal to 1, so that means that there's equal probability of photon going in both directions, then you get a Poissonian statistics. Okay, and that Poissonian statistics essentially is for a laser. A laser, a coherent state will give you G20 equal to 1, and if the G20 is less than 1, that's what we call sub-Poissonian. And in that case, you are already started seeing the signature of quantum nonlinearity. So if you do an experiment, you have a light coming in, a laser, it goes through this cavity and emitter system. In the output, you started with the laser, your correlation was 1, it's a Poissonian system. But now if we go to the in the transmission, like in transmitted photon, you're getting G20 less than 1. That means that you have more single photon in the system than what you had before, and that takes you to the sub-Poissonian regime, which is a signature that there is an interaction between photons. And super Poissonian is G20 is greater than 1, and this is actually turns out to be a thermal state. So the state that comes up from your light bulb actually falls into this, and this is not necessarily super useful for quantum computing. So our goal is to really go to this G20 and make this G20 goes to close to 0. Here I would like to point out that this experiment sounds very similar to single photon source. In single photon source, you actually pump an emitter system at higher wavelength, and you collect the photoluminescence from the single emitter. That can be quantum dot, can be NV center, and you are also looking for G20 equal to 0. If the G20 equal to 0, then you know you have a very good single photon source. But there is a very big difference between that experiment and this experiment. In that experiment, you are pumping the system, or you are exciting the system in a very, very different wavelength and collecting another wavelength. Whereas here, everything has only one wavelength. You are essentially shining the light in one wavelength, and you are measuring that wavelength. And just because photons interact with each other inside that cavity, that actually make sure that no two photon state can go out. You can only get one photon. So that's a very, very big difference, which often gets somewhat overlooked. Okay, so I think I'm going to stop here and see if there is any question before I start talking about the actual physical system. Okay, so is there any question?
Any questions, participants?
Okay.
People from physics can have a lot of questions.
Yeah. Let me know if there is any question, and I cannot really monitor the chat. I generally use Zoom.
Yeah, one question is from Dr. Rajiv Chopra. Rajiv Chopra ji, go ahead.
Yes, sir. In that quantum stack, please explain that particular thing layer, microservices layer in that stack, quantum stack.
Yes.
This one, yeah. So this micro architecture. What is that?
So this is basically, I mean, you can think about that what we are talking about in the really physical level, right? So micro architecture is now you are actually connecting many of them, So you're creating some kind of architecture. Like in this case, as I mentioned, that like this can be thought about as an architecture. That your single system is like kind of in the really new material, new devices. Then you're connecting these devices, and then you start putting this other kind of you are creating the more instruction set, and ultimately go to quantum logic. And as I mentioned, I mean, there is many different ways of writing this kind of making this stack, but this quantum simulator perfect qubits is really what the physics lies, and this is the microarchitecture is going above the physics to create like new kind of architecture. And my expertise is really on the quantum simulator side, so I cannot really tell you what microarchitecture exactly here means, but it can be very different depending on what kind of quantum system you are looking into.
Okay, sir. Thank you. Thank you.
Okay, great. Okay, so I'm going to then start talking about, as I mentioned, that we need the HBT second order correlation, and we want to make G20 equal to 0. So what are the actual physical system where you can start creating this kind of strong photon nonlinearity? So probably the most well-developed system, and this is a system that I personally worked with several of my colleagues. All of them are now professor in somewhere, and Yelena Vukovic, she's my advisor from Stanford. There are also several other groups that who worked on it. Is known as it's a photonic crystal cavity, and here you have a self-assembled quantum dot. It's a gallium arsenide based indium arsenide and gallium arsenide quantum dot. And there, this quantum dot is grown by something known as molecular beam epitaxy, and you grow it in a thin membrane. And when you have this thin membrane, you pattern cavities in this thin membrane. What kind of cavities and what do those things will probably be clear from the talk. But essentially, this is one way to make a the single photon emitter plus cavity system. And we have observed in this kind of system, which is the Hamiltonian of this system is known as this famous Jens-Cummings Hamiltonian. So you can start with an harmonic ladder that I mentioned for simple harmonic system. Once you couple a two-level system, you are going to get this anharmonic ladder structure. Okay, I'm not going to go into more details of this Jens-Cummings, but you can already see that these energy levels are not equispaced, so you can start getting some sort of nonlinear interaction, single photon nonlinearity. And we did observe this, that you can see the G20, the second order autocorrelation on this system, goes down below 1. This is an experiment that I did. Very recently, in a similar system, people have observed this G20 going very close to 0. Like you are sending a single laser, you are measuring the correlation of this laser at the output. Okay. But this problem, as I mentioned, that many of these quantum dots require spectral matching and spatial matching that remain unsolved. And today, the largest number of coupled cavities, because ultimately you have to make many of those cavities with dots, is only 2. There is like no one has done more than two of the system coupled to each other. So that's kind of a big problem in the scalability. And there is a lot of material science problem here, that how do you get better quantum dot? But to the best of my knowledge, no one has really solved this problem yet. Okay. So what can we do other than like, can we actually improve this system further? So there is one way to improve that is using exploiting quantum interference. So there is some work that I did that if we, and this is a theory work, your cavity, you put a 4-level system inside the cavity, maybe an atom, you can actually start seeing very, very strong anti-bunching. So G20 value, which is very close to 1 before, can go down to very close to 0. There's another work that I did, and we also experimentally demonstrated some of this work, that if you have a couple cavity, and again, how this cavity is formed, I'm going to discuss in a bit. But for now, let's assume this is an optical resonator. It's another optical resonator. You have a quantum dot here, and if you put a coherent state here, you actually get a sub-Poginian light out. Okay, so that means that you are having like some sort of quantum state, and quantum creates a new quantum state. This is also known as unconventional photon blockade. There's a lot of work on this, and this unconventional photon blockade inspired another work that again I worked in back in 2012, that if you have a single emitter that's coupled to 2 optical resonators, that there is no coupling between 2 optical resonators, and you can actually implement that using like this kind of optical cavities with some electromagnetic engineering, then you can get very strong anti-bunching as well. And this work actually been experimentally demonstrated back in 2018 by another group. So these are the kind of some different ways that where you can get very strong anti-bunching and you improve the single photon nonlinearity exploiting interference. Okay, but the problem that I mentioned, that it's very difficult to actually have multiple systems, with each system having the single photon nonlinearity, which remains still unsolved. One option is using bulk optical nonlinearity. So every optical system has optical material has some sort of nonlinearity. Okay, so if you exploit the nonlinearity, and this nonlinearity is known as second order nonlinearity or third order nonlinearity, so then there's one work that came out in 2012. They show that if you have a third order nonlinearity, and silicon actually has third order nonlinearity, also known as K nonlinearity, you can actually get this anharmonic ladder structure. Okay, and that can give you the photon blockade that's what's shown here. With collaboration with Girase, actually I wrote another paper back in 2013. I showed that if you use second order type nonlinearity, you can also get the single photon nonlinear interaction, but in the quality factor is you need a smaller quality factor, because Chi2 is effectively a stronger process than Chi3. So overall, with a lower quality factor, you should be able to get this single photon nonlinearity. Okay, but if you look at the cavity quality factor, it's still pretty large. So even though you get the scalability, because this is just based on cavity, you don't need to put any quantum dot or any quantum emitter in these cavities, but your quality factor that you need is very, very large. It's just impossible to get like that kind of high quality factor. I probably have not mentioned, but the quality factor essentially means it depends on the line width of the resonance. So anytime you have a LC resonator, right, you get a line width. So in optical cavity, you can get a line width. Any resonator has a line width, and that line width has to be really, really narrow, which is very difficult to fabricate. Now there is some very promising work that came out only 2 years back, but they showed that if you actually have a quantum well-like system, so quantum well is a two-dimensional system. It's not a quantum dot. So that the main difference is in quantum well, your electron and hole wave function are confined only in one direction, and it's free to move in 2 dimensions, whereas quantum dot, this electron and hole wave function are confined in all the 3 dimensions. I'm pretty sure in quantum you have probably looked into particle in a box. So in the particle in a box, what is the box dimension? That's what we're talking about. So for a quantum dot, your box dimension is 3 dimension. For quantum well, the box dimension is 1 dimension. So you confine in the z height, but it's your electron and hole is free to move in plane. So the quantum well system, but using a very, very confined photonic mode, and in this case they did it with the DBR kind of a mirror and with a fiber, and that's why from the optical resonator. Again, as I mentioned, for optical resonator you need 2 mirrors. One of the mirror is the distributed Bragg reflector. That's what they make it. The other mirror is coming from the fiber distributed Bragg reflector, and using this they showed that you can start getting quantum signature. Okay, so you can see the G20 value is going below 1. It's definitely very close to 1, but with the statistical significance, they showed that indeed we can start getting into this single photon nonlinear regime. And this is actually very interesting, because quantum well or 2D material, you can really place it on a very large substrate. They have very similar frequency. There's a broad emitter. And then if you can make this cavity, the cavity engineering is much simpler. It's a lithographically defined system. We have much more control over that. Then we can really create a scalable system. And that's what this paper talked about. But it's not quite clear that how do you make this fiber cavity really scalable. Because these are not really on chip. I mean, it's a pretty small cavity, but it's still not on chip. So our strategy for quantum simulation with correlated photons, and that's what we are working on at University of Washington, is use integrated photonics. We're using integrated silicon nitride photonic resonator. We can see that these are all, each on one of them is a cavity. So here is a 10 cavity, but we can make many cavities. and develop local tuning mechanisms. So you have to tune each cavity very locally. So that's where the integrated photonics comes in, and then engineer the single photon nonlinearity using two-dimensional system. And this two-dimensional system is this atomically thin material, like graphene-like material. We're using material called transition metal dichalcogenide and some solution process material, and we confine the electronic and photonic wave function to enhance the optical nonlinearity. So that's kind of what we are working on in my lab, that we're using integrated photonics to get the scalability and tunability and looking into new material system. Okay, so with that background, I'm going to talk about kind of three topics today. One is what is integrated photonics, right? I think many of you probably are not super familiar with what integrated photonics are. I'm going to show you what is possible. Then we'll talk about some of the work that we are doing with 2D material plus cavity, and then some of the work that we are doing with solution process material and cavity. Okay, these are the three things I'm going to talk about. So let's start with integrated photonics. So integrated photonics, like integrated circuit, it really allows bring optics from table to on chip. So if you go to any optics lab, you know that there's an optics table, and you have many mirrors, lenses, objective, polarizer, many different things, beam splitter, right? You also have fiber. We can bring everything on chip made of silicon or silicon nitride. Okay, so fiber is like waveguide. We can have the gratings is like this kind of periodic structure. You can shine light from top, and that grating will allow the light to go to the waveguide. Is like a mirror. We can have a beam splitter. We can make directional couples with some of the work that we did. Some multi-mode interference tree, that is an array of beam splitter. And these are like just some devices. But essentially, the point is that today we can, by optical engineering, okay, by photonic engineering, we can create almost any kind of optical component that you see in table on chip. Okay? So we can have an extreme reduction in size. So the two things that I mentioned, that we need to have resonators, right, and emitters. So let's talk about resonator. That how do you build resonator in optical, in integrated photonics, and how you, I mean, I show you some pictures already, but how they are actually a resonator. Okay, so the resonator that we use is known as photonic crystal resonator. So photonic crystal resonator essentially means that you have a two-dimensional slab, like just a slab, and you drill hole in that slab. Okay, so you have a two-dimensional array of different material index, and in this photonic crystal, let's say you have an emitter here, and you have a photonic crystal here. If emitter emits light, all the light are going to reflect, like if all the light that is getting reflected at each interface. We know that light, when it goes from one medium to another medium, there'll be always some reflection, right? So you are essentially taking a material system, let's say a silicon nitride, and you are drilling hole. So you have the light is going from silicon nitride to air. Okay, so at each interface, light is going to get reflected, and if all this reflection add up constructively, then light cannot propagate. Okay, so this effect is known as distributed Bragg reflection, and with this distributed Bragg reflection, we can make very high reflectivity mirror. So essentially, as I mentioned, for any cavity, you need mirrors. You need many mirrors to make sure light is confined, and this photonic crystal gives us a way to make mirrors. And not just in one direction, in multiple different directions, light can get confined. Now in the slab, your light can get also confined by total internal reflection. You have a slab, so we know that light is from this emitter, light is going to come in different angles. Something is going to lose, but some of the light, as you know, is going to still be confined in the slab by total internal reflection. So if in a slab of photonic crystal, if we remove some of these holes, like we created some holes, but then we remove some of these holes, what happens here, that if you have somehow trap a light here, this light in two dimension cannot propagate due to distributed Bragg reflection, and out of plane it cannot propagate also because of total internal reflection. So the light is going to remain confined in a small volume in this photonic crystal platform. So that's the basic idea. There is another way to explain this behavior by assuming that this photonic crystal essentially creates an optical band gap, very similar to the semiconducting system, And if you introduce a defect state there, it stays in the band gap, and the band gap, it essentially cannot go anywhere because there is no available state. So there are several different ways of explaining it, but the whole point is that by removing some of the holes, we can create an extremely small mode volume optical resonator. So how does it look like? So if you, this is an optical resonator, and you can then simulate this system like using finite difference time domain, and this is what the mode profile looks like. Okay, so you can see this is the features of 1 micron. So you are actually storing light in a very, very small volume, and whole structure is of course very small, and the small volume confinement is very important because that gives you very strong light matter interaction strength. Now, not just 2D, we can make it into 1D photonic crystals. So this is kind of some of the structures that we fabricate, and your light is confined here. And not just, we can change the confinement to air or material system depending on design. So the whole photonic crystal is a huge body of literature, and this research is ongoing to design new kind of structure to store light in a smaller volume, maybe with high Q. Maybe you want to store light in the air, not in the material system. So there's a huge amount of work that goes on, and you have a huge amount of flexibility. There's also like some work that's happening combining inverse design, that essentially means optimization, machine learning to design this structure. That's one of the some pioneering work came out from my advisors group. But this way you can actually confine light inside the cavity. And the other cavity that we use is called whispering gallery mode resonator, and it's kind of looks something like this. Is a micro ring resonator. So light comes from the waveguide, get evanescently coupled to this ring, and it keeps on traveling, and that's how your light can get stored. Okay, and it can be also like something called micro disc or micro ring. So two different type of resonator. It's called whispering gallery mode because it turns out that some of this big cathedral back in Europe, people realize that sound can travel in this gallery. Because if you whisper to someone, a person that's very, very far from you sitting on the gallery can hear what you are saying, because sound wave travels and it essentially creates an optical resonator. That's how this whispering gallery idea came out, and of course we are doing it for the light. Okay, so these are the two kind of resonators we are going to use primarily for making resonators in integrated photonics. So I mentioned we want to make couple cavity array. How do you make couple cavity array? It's pretty simple. You just take two cavity, and you place very close to each other. As I mentioned, it's electromagnetic wave. So electromagnetic wave from one is just going to leak out to go to the other one. So by bringing them very, very close, you can create a coupled platform. So if you zoom into this, okay, you can see this is how our cavity is. Now this structure, if you just look at what happens, these are called grating. So most of the structures are still probed in the free space. We can shine light here. Light will go through this waveguide. Okay, this is where my cavity is. So I think this is actually cavity is not here, and then it comes out, and we collect it from another grating. That's how you can create the optical couple cavity. These are two cavities. We can go to 4 cavities. So in this case, you can see 4 cavities coupled to each other. This is the so by the way, these are the pictures that are taken with the electron micrograph, the scanning electron micrograph. So we have a very, very high resolution. You can see that we can see these holes, and each of these holes are like in the 100 or 200 nanometer length scale. So we fabricate these structures using electron beam lithography, and then of course we test it and we fabricate them using etching, which are not going to go into more details. And you can actually probe this cavity mode. So you can see here that if you have small spacings, so if the space comes to very, very close, that essentially means you have very strong coupling, and that coupling is going to give rise to mode separation, mode splitting. But if you have a larger spacing, then the coupling strength goes down, and you can see all those cavities nearby. But the whole point is that creating this kind of couple cavity array in this system, which generally requires a huge amount of resource, if you are doing that in macroscopic system, it's very simple doing in solid state platform using integrated photonics. We can make many of those. This is like an example where each cavity we can probe. There are 10 of them, and you can see these 10 optical resonators. Okay, we can probe each of them. So we fabricated the structure in our lab. This is a little bit detail which I'm not really going to spend too much time on, but you can actually doing topological photonics using this system. So you have this couple cavity, and there's a lot of work going on in topological photonics for quantum simulation, understanding this topological physics in the quantum regime. So there is a one famous model that is known as SSH model. So in SSH model, you have like a couple node, but the coupling between different node are different. So between A and B, you have a different coupling strength than between B and A, and depending on whether J1 is greater than J2 or J2 is greater than J1, you can get a trivial topological system or non-trivial topological system. So this is the trivial one. Actually, you open a band gap. In non-trivial, in topological, you get some modes in this band gap, and this is a slightly different band gap, and there is some strong correlation, like it's the same electromagnetic system, but I'm not going to go into more details. But it turns out that if you actually have a topological photonic bath, that is useful for various quantum simulation problems. Okay. And one of the things that we recently did, we actually created an couple cavity system. You can see there are like 8 cavities. These cavities are coupled to each other. These are like kind of this is a whispering gallery mode cavities. It's also known as a racetrack because they look like this horse racetrack like structure. They couple in this coupling regime, and we can engineer both trivial and topological photonic system. We actually experimentally demonstrated that. This is one of the first demonstration to show that we can actually have all these modes. We can probe it. We can get this topological, the trivial band gap opening up, and these are all done using silicon photonics. These are fabricated in-house in the university, but there is ways to really make it to a large-scale platform. I mean, some of you probably know Intel has a huge push for silicon photonics, not for quantum, but they're also looking into quantum application. Psi Quantum is really working on silicon photonics. Xanadu are also working on silicon photonics for this. But yeah, so there are things that you can do with this couple cavity. But really, the take-home message for this is that once you go to solid-state photonic system, you can really gain benefit from small size, and there's a lot of flexibility in terms of what you can engineer. Okay. How do you tune them? That's a big problem because one of the issue with integrated photonics is once you make it, it's lithographically defined. You cannot really change it. So one of the changes is thermo-optic, and that's how most of the work in silicon happens. But as I mentioned in the beginning, our goal ultimately goes to silicon nitride, because many of the emitter systems that I mentioned, including NV center or silicon vacancy center or quantum dot, they don't really emit they will be strongly absorbed in silicon. So if you are going to make this platform, integrated photonic platform with this material system, it has to be made with silicon nitride. So we developed some thermo-optic tuning, and thermo-optic tuning of silicon nitride is very small, but we actually created put polymer on top of it, and we show that it's indeed possible to change the cavity resonance by a large amount. Okay. So this is enough to have all the cavities resonant. So as I mentioned in the beginning, if you want to make a quantum simulation, we have to have all the cavities close to each other, and using that, we can create this couple cavity array platform. So we are developing a lot of technology to go there. Another problem that I mentioned before, that with integrated photonics, is it possible to couple two distant cavities? In terms of, yes, it's possible. There is some work that we are doing with like this. This is a kind of one kind of nanobeam kind of photonic crystal cavity, 2 photonic crystal cavity, but we couple them by a ring resonator. So these 2 cavities don't have to be placed very, very close. By coupling them with another resonator, we can actually decouple the coupling strength and spatial location of this cavity. And these are kind of some of the fabricated structure. You can see here, we have a waveguide with nanobeam cavity and ring resonator. This is the coupling regime. So we can really fabricate this structure. This is something that we are working on nowadays. There are many other tuning mechanisms. One of the tuning mechanisms that's getting a lot of traction is something known as phase change material. So I mentioned in the beginning that we are actually working with Intel on this phase change material for quite some time. So the phase change material undergoes a phase transition. It goes from amorphous state to crystalline state. To going from amorphous to crystalline, you have to do uniform heating greater than 100 nanosecond at 200 C, and then you use a pulse of 10 nanosecond, and you really melt the material, the crystal material, you melt it, and you quench it to go to the amorphous state. And in this kind of material system, you actually get very large index change, and it's a non-volatile change. And some of this work is actually very well understood for phase change memory, but we are using that for optical system. This is kind of some of the devices that we fabricated, and we showed that it's indeed possible to bring some of this phase change material to wavelength range. This is the wavelength. This is the wavelength where most of the silicon vacancy or nitrogen vacancy centers they emit. So it's possible to really start tuning in the visible wavelength range. Okay, so I mean, before I go, I mean, I think the main take-home message for this part of the talk I wanted to get through you is there is a lot of integrated photonic technology that exists that is fabricatable, that we can design to significantly miniaturize the optical system. And there are like some work on the reconfigurability that we can look into to ultimately make sure all the cavities come at the same resonance frequency. Okay. So I'm going to maybe stop here again, see if you have any question before I go to more material oriented stuff. So is there any question?
Yeah, anybody having any queries?
Okay. Any question? If not, yeah, okay, great. So if not, I can go back. Can you still see my slide?
Yeah.
Okay, great. So now we'll talk about some of the work we are doing for the 2D material cavity QED. And by the way, these are the papers, and all these papers are available from my website. So you should be able to download it and read it if you have. And if you have any question, feel free to send me an email, and I'll be happy to answer those. Okay, so let's look into the 2D material cavity QED stuff. So 2D material, okay, it really doesn't require much introduction. It's, I mean, all of you know the graphene got a Nobel Prize, and there is like a huge body, almost a field on its own, that it's kind of atomically thin material that people are looking into. So graphene is definitely the most well-studied material, but by now people actually have figured out some insulator in this system, semiconductor. People have looked into MOS2, looked into black phosphorus. So various different systems for this 2D material that exists today. The material that we are primarily interested in is this transition metal dichalcogenide. These are actually kind of MOS2 is one of the examples. It's a semiconducting system. These are all atomically thin material systems. So in case you're not familiar, so just think about every material is three-dimensional, and imagine that you can take the thinnest slice that you can take of this 3D material. The thickness of that will be atomically thin, right? Because at least there has to be some atoms. So that is called the 3D material. Okay. So the excitonic system has large excitonic binding energy. Large excitonic binding energy, and we don't require any explicit lattice matching for this material system to put it on a silicon or silicon nitride. So as I mentioned in the beginning, the people are working with quantum wells, but all these quantum wells are made of this gallium arsenide or some kind of 3,5 material system, and that requires lattice matching. You cannot just grow this material on any substrate. But in this 2D material, you can just place it on any substrate, and that way you can get a quantum well-like functionality in silicon or silicon nitride platforms. This really opens up a huge opportunity for us to do new kind of light matter interaction, designing new light matter system. So in my lab, we looked into this 2D material integrated optoelectronic devices for a long time. So we looked into some of the work in the graphene, like one of the first work on graphene silicon modulator, then detector. We also looked into some optical switching. We are looking into optical lasers. We had a paper back in 2015 in Nature. We had a cavity enhanced electroluminescence. We also can do cavity enhanced second harmonic generation. So there is a huge body of work that exists from my lab on 2D material integrated optoelectronic devices. But all this work are really were in the classical domain, and we wanted to understand that is it possible to go to quantum regime, and that's what we are focusing on maybe last 3 years. So one of the work that we first did is, okay, our goal is to get to the single photon nonlinear optics. Is it possible? So the system that we envision, and this is a theory work, we actually think about a nanobeam structure, and we put a 2D material on top on this nanobeam, and we wanted to understand that, okay, what we get from this system. So it turns out the Hamiltonian that describes this system is given by this term, okay, and UX. So in this case, A is the photon, and B is the exciton. Now, I mentioned that this excitons are two-level system, but in 2D material, as the exciton is free to move in 2 dimension, that essentially means you can create many excitons. So the excitons kind of behave as almost like a bosonic system or like a cavity. So it's kind of coupled resonator, but you still have some interaction, U sub x. That's what you wrote here. You can show that the G, the light matter interaction strength, is actually proportional to, forget about this prefactor for now, let's do this one, is S sub x over S sub mode. So S sub mode is the cavity mode area and S sub x is the excitonic mode area. Whereas U sub x, the nonlinear interaction strength, is inversely proportional to S sub x. So by reducing the area of the 2D material, we can have very strong nonlinear interaction. And that's what we need to go to this quantum nonlinear regime. And we actually theoretically analyze this system. And this is a paper that got published in PhysRefB. And what we found that indeed you can get this anharmonic structure. And this is what the G20 look like, right? That there are many points across the wavelength. Like you're putting your laser in different point and you're measuring the correlation. Your G20 does go below 1. And if you actually turn on the actual loss, right, those loss still keep some of the point where your G20 is pretty large or pretty small, like G20 goes very close to 0. So this really shows that there is a possibility of getting into single photon nonlinear regime using this kind of 2D material plus cavity platforms. This is what we demonstrate theoretically, and there is some more details that we actually, to make it more close to experiment, we also assume that how the dipole decay rate is going to change. Okay, so those things we have looked into at greater details in this work. But when you want to make this system, right, I mean, we have to fabricate the structure. It turns out that there is a lot of issues with this kind of more engineering problem, if you call it. And one of the thing was, so in this case, you see there is a chip. We fabricated many optical resonators. The small ones that we are seeing here, I'll show you a bigger picture at some point of time. This is actually a microdisc resonator. It's a very small one, but we can make many of them. But when you transfer this 2D material, the way the transfer process generally works, the conventional transfer, you actually transfer many other things on the chip. And that's actually not very useful, because ultimately, as you can see, we want waveguides, we want to make sure light goes on chip. Any kind of residue can completely kill the transfer process, kill the light emission. So to solve that, we developed a new method where we actually create this dome, and we melt the dome and pull it and create a kind of very small needle-like structure, and we can pick up very small 2D material. So this is how it looks like. This is the before, that was the structure. Now this is the structure. And if you zoom into it, you won't see it, but there is essentially no other residues. And this was a very important step, in our opinion, to have very clean transfer of 2D materials. Okay, so we can actually really transfer material on nanophotonic structures. So you can see there's a 4-ring resonators, and we transfer one of the 2D material here. This is an SEM. This is one 2D material. This is another 2D material. So we can transfer different 2D material on different cavities. So these are kind of very interesting technology that we developed to really build this platform, and we are still working on it. There's a lot of unknown problem that we are learning more and more. One of the things that we realize, when you have very clean transfer, that there is some interesting physics that pops in. One of the things that we found, that if you actually put 2D material and we measure something that known as photoluminescence, okay, photoluminescence means you are pumping the system at above band, and then you in the exciton frequency, your light, it's going to emit light. And actually that's how most of the optically pumped lasers are really built, like you do photoluminescence. There is an asymmetry. You can see the modes pops up much more prominently. So this is my excitonic peak at the great detune side, and these are all our cavities. So is there a question?
No, it's okay. Carry on.
Yeah. So these are ring resonators. So ring resonator are many modes. So you can see the modes primarily get populated in the lower frequency. This is the wavelength. So larger wavelength means lower frequency than the higher energy. And this is what you can see. But this is not really clear in the transmission. So when you are having photoluminescence, that you are exciting your electron hole pair in a higher state, and then they are decaying and coupling to the cavity, we hypothesized that there is a role of phonons. And to understand that, we actually added these new terms in our Hamiltonians. This term you already see, this light-wire interaction term, this is a driving term, but we model this phonon-mediated interaction with a deformation potential, and we show that it's indeed true that once you have this kind of this term turned on, if you have no term turned on, this is where my exciton is, the cavity population, either the cavity is at higher energy or lower energy, remains same, but once you have this phonon-mediated structure, you are going to see some sort of asymmetry, and this asymmetry goes away as you bring them closer. Okay. And if you change the temperature in two different temperature, you can, the asymmetry also goes away. So essentially we showed that it's indeed possible, and we see this in experiment, that as you increase the temperature, we start seeing a more symmetric behavior, but with the lower and lower temperature, all the modes generally pops up in the lower energy side. And this paper was recently published in this the Nature Partner Journal. You can also get an archive preprint from this paper, and also is available from my website. So we looked into this kind of, so really this model needs to be changed. And we are really understanding this kind of system. There is a lot of unknown physics. We are trying to build this platform that I mentioned for quantum simulation, but we are still kind of trying to understand, okay, what are the physics of this system? One recent work that we did, we actually have a nanobeam resonator. So you can see here, and we transfer our cavity. This is our cavity. And this is the first time we actually, someone showed there is a role, there is a coherent interaction strength measured between one of this very, very small mode volume cavity and 2D material. And the way we prove that is we actually change the temperature of the system. So if you have no 2D material, your thing gets like almost in the same resonance. There's very little change in the resonance frequency. But if when you have 2D material, you see a much larger change of your cavity resonance, and you can fit that data, right, from a cavity QD system. So you can fit it, and we found that the nonlinear interaction strength, sorry, light-wire interaction strength comes out to be around 4.3 millielectron volt. Okay, so this is actually pretty interesting. This paper is still in archive. It's under review right now, but this is the first time someone measured the coherent light-wire interaction strength, and we believe we are very close to the strong coupling regime. Taking back a little bit different topic on this, that I mentioned that we need this exciton polariton. So we recently demonstrated exciton polariton in a metasurface based structure. So the metasurface, as I mentioned, is it's kind of think about like a 2D slice of a metamaterial. So 2D material is a 2D slice of an actual material system. But if you have a metamaterial, like you have sub-wavelength features in 3 dimension, you take a 2D slice, you get a metasurface. And my group is doing a lot of work on metasurface for imaging. We even have a startup that's trying to commercialize some of this technology to create very, very small sensor. But here we try to understand, okay, can we actually look into some of this metasurface and engineer some resonator? And indeed, it's possible. So in this case, we have a metasurface. It actually supports a very kind of moderate Q resonator. And then we put 2D material and we see this anti-crossing behavior. The anti-crossing behavior essentially means that we have strong coupling. So from there, we can also estimate the light-wire interaction strength, which is like one of the very first time, like this experiment required like DBR resonator do like most of the work, but now we are doing it with a single, like almost micron scale thick resonator. And this really opens up a lot of opportunities for new platform development, because the 2D material is on substrate, so we can actually now pattern electrode, so we can control the resonance frequency. If we get this exciton polariton and stacking multiple stack of 3D material, it is possible to look into something that known as exciton mediated superconductivity. So there's a lot of new quantum states that can be created using this kind of platform. Okay, so let me just go over the solution process quantum dot, and then I think we can stop for questions and more discussion. So the another material system that we are working on is the solution processed colloidal system. So colloidal system is very well developed system for classical application. Okay, and our goal is this colloidal system, can we combine it with nanophotonics, integrated photonics, to create better single photon source, single photon nonlinearity, maybe even spin physics. So this colloidal material is, you probably already know, but a huge application in solar cell are done with the perovskite quantum. The perovskite material is like one of the solution process system. People are also looking into this kind of material system for LED, like especially like you probably heard QD LED TV from Samsung. Those quantum dots are this quantum dot. But primarily the application area of this quantum dot has been in the classical domain, not in the quantum domain. Okay, so we are trying to see, can we actually use quantum domain, bring this material and do some interesting physics. Okay, so one of the problem initially was that, okay, how most of this nanobeam cavity that I described is are floating, so they are actually suspended, so they kind of sag, right? If you start doing some solution processing, you can break this cavity. So we created some mechanically stable encapsulated silicon nitride nanobeam. So this cavity actually sits on a substrate. There's a lot more nuance to this that is actually very difficult to design, and we spend a lot of time designing this kind of silicon nitride photonic resonator on an oxide substrate. This is how it looks like, so you can zoom into it. And key idea was to create an elliptical hole. So these are kind of detailed in this particular paper. So once we have this kind of optical resonator, we asked ourselves, okay, is it possible to deterministically position the solution process material on the cavity? And to do that, we actually came up with this idea that we will make the cavity, we'll cover the cavity with a polymer, and in the polymer we are going to drill a hole. Okay, so for example, let's say you have 3 cavities. This one doesn't have any hole, so quantum dot sits here, like, and then you put quantum dot everywhere. The quantum dot sits here, there is no coupling between that. Here we created a hole, so quantum dot can go in and couple to cavity, and same for here. Okay, so by creating a hole on the cavity in the polymer, or not hole, we can actually get the quantum dot cavity coupling. Okay, so we showed that in experiment. So this is like, if you this is a system here. So if you have no hole, like you shine light, we're doing photoluminescence and collect from this grating, you just see the quantum dot PL, because there is always some light, the quantum dot is everywhere. But the moment you make the hole, you start seeing this cavity resonance. So we can control now by the coupling between the quantum dot and cavity by the solution process system, and really creating this kind of new cavity geometry. Okay, by controlling the size of this opening, we can also control the number of quantum dots. So this is what we showed here. We have not been able to get the single quantum dot regime. That is something that we are currently working on. But if you go to the single quantum dot regime, then we are really in this quantum limit. We can create the single photon source in a much more deterministic way than what has been possible with any other single emitters. We also measured partial enhancement. I'm not going to go into too much details, but essentially a partial factor tells you how fast the emitter decays. Like, you can enhance the emitter emission rate by using optical cavity. And as I mentioned in the beginning, in cavity QD, you have a bad cavity and good cavity regime, and we are seeing the signatures of the good cavity regime where we are in this system. So we measured those things to really show that actually we have coupling and we are changing the lifetime. Okay, but I mean, one thing that I mentioned before, that this coupled cavity, I mean, this is what really kind of where integrated photonics becomes very, very interesting. We can make cavities very, very small. We can engineer coupling between them. Using that, right, what we showed in one of our SCS photonics paper, that we can actually now improve the single photon indistinguishability. And this is it turns out that all this linear quantum computing, like the boson sampling or the work that Xanadu has done, you require the single photons to be as indistinguishable as possible. And this is one of the big problems of the solid state system, because the single quantum dots or single photons are always distinguishable. And colloidal quantum dots specifically, you have something that's known as a very large dephasing. So these quantum dots have big problem. in terms of the indistinguishability, and we showed that we can actually enhance the indistinguishability significantly, as you can see in the table. This is a self-assembled quantum dot in a single cavity. This is a silicon vacancy center in couple cavities, and then the colloidal quantum dot in couple cavity, and this is the optimal system. Can experimentally okay. So I'm kind of almost in 1 hour, 1.5 hours mark. I'm going to kind of maybe summarize what I told you, tell you like where we are in the quantum simulation, and then maybe we can discuss more. I'll keep some time for question answer. The integrated photonics really provide us a way to make a scalable way to integrate many devices, not just resonator, but resonator is one of the things that I focused on chip. We can make extremely small resonators. We can make them coupled to each other. We can address each one of them. We can decouple the distance and coupling. I showed you some result, but as such, the integrated photonics provides a lot of interesting avenues to really scale up the quantum computing. Okay. And then I told you about 2D material cavity QED. So this 2D material hosts very robust excitons, and it's a 2-dimensional exciton. There is quantum confinement. It's not 3-dimensional confined, but confining them to very, very small mode volume resonator is indeed possible to get to single photon nonlinearity. That's we show in theory. We're doing an experiment. And as we have the single photon nonlinearity, if you can make many of these cavities, it becomes a very interesting platform, because that's when you can start really thinking about doing quantum simulation with this kind of system. Okay. Finally, we told you about the solution process system, and show the deterministic positioning. We know that we can put actually single quantum dot. We have designed some new quantum dot. This is our collaborator in chemistry. They can create something that's known as giant quantum dot. It's a quantum dot, but it's actually large physical size, and that way we can put a single one of them, and then we can, using that, we can do like a hopefully like a scalable single photon source. And so, as I mentioned, we started with the towards photonic quantum simulation, and we believe that these 3 problems, of course, not everything is solved. That's why we are still towards. We don't have a photonic quantum simulator. And I would like to highlight here that there are a lot of work going on in the wave physics. People are simulating wave physics, that people are using some topological physics. Those are not quantum, because those, like light, behave as wave classically. These are not really quantum. But really, to go to quantum, you need the single photon nonlinearity, and I showed you like some of the work that we did, and it's a very difficult problem in some way. It's a very difficult physics problem for sure, and there's not a good solution. But I also showed you the scalability is something that is really solvable in optical system, and the tunability is also, I think, is well within our reach. We are already seeing effect that we can make different cavities resonant to each other. So then we have to solve the single photon nonlinearity. And the single photon nonlinearity, even though I really motivated it in terms of quantum simulation, even for quantum computing, the photonic quantum computing, if you really can engineer the interaction between single photons, it will improve the scalability significantly of this platform. Okay. So I'm going to stop here and see if there is any question from anyone. And okay.
Anybody having any queries?
There is someone's hands up, I think.
Yeah, you can ask questions. Okay.
Yeah.
Hello, am I audible, sir?
Yeah, I can hear you.
Okay. Sir, my question is, what is the application of QD coupling in context of cryptography?
So from the cryptography, I mean, you need these single photons, right? I mean, that's kind of where some of the application you can think about that. Ultimately, if you are doing a photonic quantum, photon-based quantum cryptography, you have to create these single photons, right? So right now, if you use these single photons using parametric down conversion, your rate is megahertz. If you use this kind of solid state system, you can push this to like gigahertz. So you can get a huge enhancement in terms of data rate using this kind of system.
Right, sir. Right.
Yeah.
Thank you. Thank you.
Anybody else? People from Department of Physics? Or those who are working in photonics?
Yeah, so this is definitely not, this talk is not for computer science audience. Some of my other work on the nanophotonic sensors is generally I work with a lot of computer scientists, but yeah, the quantum work in my group is very much physics focused.
Yeah. So that we witnessed just now. Anyone participants who like to have like to ask any questions, then you can please ask. So I think there are no questions as such.
Yeah.
So if you have anything to share, you can continue, or otherwise we'll conclude here.
Yeah, we can conclude. And if you have any other question, feel free to send me email. Okay.
Yeah, definitely.
Okay. Thank you.
So thank you so much, Arka sir, for your wonderful session, giving your valuable time to us all the way from US, Seattle. Thanks a lot. And
Thank you.
Namaskar, sir, and good night, sir.
Yeah. Good.
Okay. Take care, sir.